avec un grand plaisir d'être ici. And now I will switch. I still kept these days to have it in my memory, to remember the day in which in Lille it was big shower with snow, yeah, and in the moment when nothing was working, yeah, no buses, no trains, no metro, nothing. So, it is well known that the properties of the materials are strongly dependent on their size. Since we are dealing with catalysis, and we are especially interested on the surface atoms, yeah, we know that there is such a relation between the surface atom and the bulk atoms. What I will try is to demonstrate how we can use this kind of materials from the atoms to larger agglomeration in catalytic application. And what I will start with the first example is dexterous hydrogenation. If you look in my CV, you will see that I was dealing over the years with many kinds of catalysts. In fact, I'm interested on the reaction, not on the catalyst. Then, after I decide, I select a certain reaction, I try to adapt and to find the catalyst who can do the job for that reaction. So, in that moment, we were very interested in this subject to look for the diester selectivity. Prostaglandin intermediates are good for almost everything. All the kind of diseases are using such kind of compounds. So, but the problem with this kind of of the reaction, yeah, is the fact that here, yeah, you have to hydrogenate this molecule, and only these compounds, yeah, only these compounds from here, yeah, it's active. So when you hydrogenate this kind of structure, yeah, you have to keep, yeah, the double bond, CC double bond unaffected, and you have to hydrogenate only the CO. Something which you know very well from the cyanamaldehyde story, yeah? But here it's a more delicate situation, because in that case you look for the preparation of flavors from cigarette, while here, yeah, you are doing for the preparation of pharmaceuticals from humans. So in that moment we thought, okay, let's look for the effect of the mesoporose, and we started to check the effect of two kinds of famous mesoporose materials of that time, MCM41 and MCM48. We look for the effect of the precursor acetate, chlorine, amines for the ruthenium. We look rapidly for the preparation procedures. And what we have done is that moment it was to be sure that ruthenium is inside. We had a nice cooperation with Max Planck in Mülheim. So Per Tesche was able to cut the pores of the mesoporose, so to open the mesoporose like this, and to see what is inside of the mesoporose materials, and indeed ruthenium was well dispersed. And based on this, yeah, we tried then to look for the properties of these materials. And there is one thing which is always very strange in people doing organic chemistry. People doing organic chemistry, it's something we started also here. They are using 5% noble metal. They are commercial catalysts. They are looking to them, and they say, okay, this is good, this is not good. And in most of the cases they are wrong, because you have sometimes not to have really 5%, as I will demonstrate now, or in some cases, yeah, you have to do a properly treatment to achieve some special properties. One of the properties which is extremely important is, as you know, and I will come back on this subject based on the gold, it is the size. And one of the possibilities, except to microscopy, to be sure of the size, is to look for the dispersions. And if you look to the conversion selectivity and an anti-ODR selectivity in this reaction, you found that you can have, yeah, even 100%, to the selectivity, which was very good at that moment. It was just at the beginning of this investigation. 80% conversions, and but this was achieved, for a certain ruthenium 0 to ruthenium 4, so a certain state of oxidation of ruthenium, and also for a certain dispersion. So now look to other properties, and again, all the time looking for the oxidation. So what you see, you may check, and here I presented just another situation that I will come back to describe it. You have to have a certain reduction degree and a certain dispersion, I also showed yesterday, to achieve good properties. Here it was another challenge, we have to perform. Because the idea, what we found in the literature, I said it's normally use a larger amount of larger loading. But here we change the ruthenium precursor, and instead to have normal inorganic compounds, we use ruthenocene. And we get the dispersion, which I already showed you, and the reduction oxidation for much smaller loading of the metals, and in such a way we achieved, I will show you, very good, selectivity and 100% yes, selectivity. So it was the first real example with smaller loading of the metals than usually, just on the fact that you assure the desired enantiomer selectivity. Now, looking for the effect of the support, we change looking for the different support like ruthenium L or ruthenium Z75. Here I will come back. There are two possibilities to control the selectivity. One is to work, in this case, it's clear that working with such loading, ruthenium will be not inside of the pore. Ruthenium will be on the external. In the case of mesoporous materials, I already demonstrated we were able to introduce the methanol inside of the pore. Inside of the pore, you have another advantage controlling the selectivity is the shape and the size of the pores of the mesoporous. In this case, to control the selectivity, you need another factor. People doing homogeneous catalysis, they are using ligands which induce some constraints, to provide the best cheminsertion and possibility to connect to the metal. In this case, we have done also exhaust measurements to see how the size and the neighbors ruthenium are changing. And again, you may see that from the preparation, in this case, you have part of the chloride. Here there is also another dream which I suspect that was already ended, and this dream was working with noble beta, you have to reduce to zero oxidation state. It's not the case, because you'll never have really 100% reduction, because you have to bound in a way your metal to the support, and then, depending on the states, you can control, as I said, the selectivity. I show you what was happening with ruthenium, but we're still not very happy about ruthenium. And we put then the same question as Spindler when he discovered the famous way to synthesize metallochlor. And he said, why not iridium? And in that case, we moved to move back to beta zeolites. With ruthenium, we were not succeeded too much. But in that case, working with beta zeolites, and I will demonstrate after that, working with iridium, you have iridium 0, you have iridium oxidized, and again the question was, which is the best ratio to provide your activity? So, we took two procedures. One is a famous Cram rule, when I already told you you can take the advantage of the course and to constrain your molecule to take a certain geometry, and in such a way you'll do hydrogenation only to CO double bond, keeping the CC double bond unaffected, or you can do an other control on the surface. So, to find the optimal catalyst, we look for the reduction temperature to control the iridium to 0 to iridium oxidized, and we got the 450 is the best temperature, something is wrong. It was too fast. We look for the nature of the support, and we found that beta zeolites, and I'll show you how many supports we have investigated. It was the best one. We look for the calcination of the support, if it has an effect or not, and we found that non-precalcinized support, and we look for the loading. Keep in mind, we are still doing now here hydrogenation of prostaglandins. And what we found is it's 1%. And look now to the question, why 1% iridium and not more? Here, you may see we check 1, 2, 3, 5, we check even more, and we check beta zeolites, ACTs, we check beta zeolites treated at 500 degrees, at 700 degrees, and we got the best results, 100% diaster selectivity, very high selectivity, again for a metal dispersion of about 18% and for a reduction degree of 25%. Look to all these other, we have difference, even for the same loading, we have difference in these values. As I told you, we check different supports, MCN, silica, zirconia, and many other, and we never got the same kind of reduction degree. To check this, we have done also XPS, but checking this point with XPS, I'll come back to this point, it's sometimes tricky. Because when you are doing XPS measurement, first of all, you are introducing your sample in the preparation room. And after that, you are doing in the measuring chamber. In that condition, at 10 minus 10 vacuum, you still may induce an additional reduction. So you have, preparing, because all the samples were introduced at the same time in the machine, you can do a comparison. But nevertheless, you have not the real value. But it was possible to make Mösbauer measurement of iridium, and this measurement is not affected by any pretreatment, and it shows again that in the case of iridium 1%, which provided the best results in this reaction, we get a certain reduction, iridium 0 to iridium 4. So here it was. What was also interesting is this measurement, and made by infrared spectroscopy. It was that we had, in addition to this, because it was beta zeolite and not other zeolites, we got a special acidity which also helped to reaction to be carried out in the way it was interesting. And this acidity was generated not by the zeolite. It was an acidity, a Lewis acidity, induced by the metal. So very soon will be, I was amazed, will be a paper in accounts Cambres, it's still under printing, it's now under the printing, of Avelino Corma, who is discussing, the effect of the Lewis acidity of many noble metals. So this we have demonstrated in the case of ruthenium, and it has indeed an importance in chemists solving such molecules, and by the presence of iridium oxidized species. Now, Why not? You have to calcine the zeolite, because when you calcine zeolite, it's proved by NMR, you induce in addition some penta aluminum coordination, and this favors the formation of the iridium oxidized basic species. So based on this measurement, we propose chelate route, in which we have on the, especially on the Lewis site induced by iridium, such kind of disproportionation of hydrogen, and this species is then selectively attack CO double bond with the formation of these compounds, which large application. Okay. Then the question is indeed the ionic acidic function of this catalyst important? And we look for another application, which was, I'll show later also, is still very important for us as application to do one pot, yeah? Citronellal conversion to menthols. Yeah. So, with our experience, we tried, okay, we said iridium is better than ruthenium. Why not to try the same catalyst? Yeah? And what we found that with 1% iridium, we have no results, zero menthol. But on the contrary, yeah, we got, yeah, the formation of this with 3%. Yeah? The same element. As I said, in organic chemistry, they will take 5%, yeah. For a company, they said, doesn't work, because here, if you look, 5% is not so good, yeah. And of course, for prostaglandins, they were completely out of the application. And what we found also, and this was pure serendipity, because we bought from the PQ this zeolite, yeah, and they told us that it is a form H, yeah, and in fact, yeah, we repeated synthesis, and you see when you are looking with H, it's not good. And after that, we were obliged to understand what is happening. The catalyst is working, and we found that in fact it's not. It's in the sodium form, and if you transform this in the sodium form, you get the same results as the catalyst. So again, we checked, yeah, to be sure, different kind of zeolites. We can check different kind of materials, yeah, and we look again for this iridium 0 to iridium oxidized ratio, and again we found that this reaction requires another ratio, another dispersion, another ratio. We have done also a SAS measurements, and again electron microscopy, and all this confirms once you have to have a certain size, and in this size of size, in this range of size, yeah, you have to achieve the reduction you need for this reaction. Now, I told you we are looking for the reaction, and very recently, in our cooperation with Professor Chemnitz in Berlin, he's an inorganic chemist, and they said, okay, we are preparing such kind of materials. Can we find an application for this kind of materials? And we said, okay, if you look to the properties, they are quite close to the properties of the zeolites, also in terms of texture, also in terms of the acidity. Why not to see if they are working in the reaction, yeah, in which we already proved, yeah, they work. So we look again for the acid function, for all hydrogenation. We started again with iridium. Iridium worked. And what we found, yeah, remember what I said at the beginning about ruthenium, yeah? To be reduced in a certain range and a certain limits, it also needs a support because the metal is creating some bond with the support, and the support should allow it to be reduced at the limit you are working. So the materials were prepared by a fluorohydrolysis, so comparing with classic water hydrolysis, yeah, you use this chlorhydric acid. Chlorhydric acid is not a red compound, it's not like chlorine. Yeah, it's still accepted nearby green chemistry, and then these are the treatments you are doing to get the release acid materials. As I said, you have surfaces and pore size in the limit of your doing for size. So these are general characterization of this kind of materials, and this to probe the infrared spectroscopy is generating this kind of strong release centers, and no basic sites, and just a second. Now going to the reaction, yeah. We follow the same procedure, yeah, what we use in the case of the iridium beta, but the property of this catalyst was very, very small. We got good selectivities, but we had very small conversion. Yeah. Again, yeah, when you use magnesium, it was even worse. So iridium doesn't work, yeah, because you can't provide it the best properties. But the question was, of course, why? And in that moment, yeah, we decided, it was the second experience we had with gold, to move to gold. And gold was prepared, yeah, using the Klein-de-Jong suggestion deposition precipitation, and on the same kind of materials we got such kind of selectivities, and we got 70%, no, 92%, yeah, comparing with series for beta, yeah, 92%, and 70% and conversion of this using gold on beta. Then we moved to the ionic fluorides. We have done XPS, and here are the results and the mechanism we propose for this reaction. So, how started my history with gold? First time I heard about, okay, it was a famous book of Professor Bond, and after that I spent some time in the laboratory of Professor Delmont. And I knew very well that Delmont was a very good friend with Haruta. And Haruta was postdoc to Delmont. And when Haruta came to Delmont laboratory, he asked Delmont, Professor Delmont, please allow me to do some reaction with gold. And Delmont told him, okay, you had never tried gold in oxidation. Please do what I recommending you to do, and forget oxidation. It's true, after he left the laboratory, he made one very famous paper in Catalysis Today, and another paper which was less cited in Journal of Catalysis, yeah, because Haruta dreamed to do this. So of course I knew. Then starts the story of CO oxidation. Everybody was interested in the conference of Limerick. Some of you maybe remember Yogoro Patak, where almost about 100 posters of gold. And at that moment I said I will never touch. After that in the conference I hear, yeah, the presentation of Echeverren from Spain, who told that this kind of Barry-Truss reaction can be realized in the presence of gold chloride. And in that moment I said, if equivalent is right, yeah, if instead to use gold chloride, I will try to make an ionic exchange of gold chloride with zeolite. In that case, I will generate ZSM5 will play like chlorine, and I will generate a heterogeneous catalyst to be using this reaction. And so these are the systems, and for comparison, I said, okay, I use zeolites also in which I will do the precipitation deposition. And which was a surprise. Working with gold exchange zeolite, I got zero conversion, and in rest, of course, it was it was a case of serendipity, because the catalyst I suggested to have no effect in this reaction led to 100% conversion and 99 selectivity. Much better, it was, and I will show you another advantage, much better than in homogeneous catalysis. So in that moment I understood that it was something wrong, because people from homogeneous catalysis, they never look to the catalyst after the reaction. They know the compounds they put in the reaction, and after that, yeah, they say, okay, I got the product. But what was wrong, the gold chloride of equivalent was transformed during the reaction, in fact, in a gold oxide, nanoparticle gold oxide. Okay, the effect of the support is again very important in this case. Working with the catalyst proposed by Avellino, Corma, gold on selenium oxide, we got nothing. It was also reported in literature, gold on magnesium but we got some results on gold on titanium oxide. And now, which was the story? Yeah, the story it was, if you look to the electron microscopy, yeah, you have again to have a very, very narrow, a certain size distribution of the gold particles. Yeah, because you know very well from the literature, because when Haruta is speaking about CO oxidation, and Graham Hutchings, the same, they are saying, okay, you have to have this size. When Avellino is looking for the oxidation of alcohols, also on gold, almost on the same support, it has different sizes when comparing with the size proposed by Haruta for CO oxidation. Again, when they move from alcohols to amines oxidation, you will see in the literature they have again other sizes, yeah? So the catalysis with gold is very tricky and very dependent on the metal particle sizes. And when you see, when we depose using the same procedure on magnesium oxide, yeah, we got much, much larger particles of different properties of gold with less uniformity. We had here in the case of beta also the advantage of the high surface of the support comparing with titanium dioxide. Then there is another importance, because people in industry, especially in the fine chemical synthesis, they are afraid to use heterogeneous catalyst. I demonstrate in the case of prostaglandin and menthol, yeah. You need a kind of catalyst for prostaglandin, and another kind. Even you have the same component, the same metal, the same support, but you need different, yeah. So they would prefer to have the same catalyst for various applications. And here, yeah, we investigated the scope, extend the scope, looking for different substrates. All these are very important as intermediate in synthesis, natural-like products. And as I said, we have very good results if you look here, and in most of the cases better than the results obtained in using homogeneous catalyst. Very important, yeah, is we are able also to do this reaction at room temperature, but of course people are interested in better results. So from room to 40 degrees is not too much. Another important point, yeah, it was the fact that to use, yeah, in the reaction unsubstituted acetylene compounds. It was very complicated in the homogeneous catalysis, and therefore they use complicated reaction systems. In addition to the catalyst, they are also using some other compounds, yeah, to allow the reaction, especially bases, yeah. So this made at the end, yeah, the reaction very red, very green, because it's complicated to extract the compound, and then you throw out large amount of the product. But working with our system, it was possible, yeah, to get at again, even at room temperature, but at 40 degrees we got 100% selectivity and 50% no, 50% yield, separation yield, and 100% conversion. Here it was one point extremely important, because again, people to apply this kind of catalyst, they don't intend to use, like in homogeneous catalyst, just once. Yeah? They need to recycle the heterogeneous catalyst. And what was happening with us? We have done the test initially with the results I already showed you, but it was just once. When we try to repeat, yeah, it never works. So I asked my student, yeah, to repeat experiments in argon. I said, you should go, you have to go. And this was happened for almost 2 months, and each time she said to me, it was not going. And one day after this time, I came to the lab. She said, I can tell you that yesterday the reaction I done was working. I told you that I was true, that it will work. No. She said, you are not at all true. Because what I have done, I was upset to repeat this and angry to repeat this experiment so many times without any results. And instead to do it in argon, she did it directly in air. Yeah? She removed. She said, okay, if you want to repeat, I will repeat, but not in the condition I have to suspend. And then it was very interesting, yeah, what is happening? And in that case, yeah, I made a connection with the laboratory from Erlangen. They have an environmental XPS, yeah? And in that environmental XPS, we check which is the state of the gold in argon, yeah? And you see it's gold in not 0, it's 1, again the oxidation state. What happens if you introduce CO? CO doesn't change compared with argon or helium. Yeah? It remains in oxidation state. But if you introduce oxygen, you generate this state. It's the story of Ekeveran. He started from gold chloride, from gold oxidation 3. In the presence of this molecule, the Barry-Trost reaction, you have a reduction from gold 3 to 1. And then, yeah, you have not to work under inert atmosphere, because you don't allow the regeneration of this. So you have a regeneration, and after that, yeah, you see she was very happy to repeat it, because she got exactly the same results, yeah, just removing inert gas. Now, another example, yeah, again from the reaction. I have a very good friend in Slovenia, Matijan Kočevar, who's interested he made some, he's interested to synthesize, his organic chemist, he synthesized precursors for new amino acids. Yeah? They are used also in pharmaceuticals, but also with some of them with some agricultural purposes. Yeah? So he prepared, all these strange are fully for the pharmaceuticals intermediates. And he said me, I would be interested to do this kind of hydrogenation. I tried with all the family of the heterogeneous catalyst, and except the disruption of some bonds, I never succeeded to got this kind of hydrogenation. Then I met Walter Leitner, And Walter told me, okay, Vasil, I have an excellent ligand and homogeneous catalyst, which we are currently doing, and he's also published 2 weeks ago another paper in Chemistry European Journal with his homogeneous catalyst. We are able to do such kind of hydrogenation, and even more we can do homogeneous. Yeah? So we took the catalyst of Walter, and we got nothing. And I'm a very perseverant guy, and I told my student, okay, rise the temperature, rise the temperature. And at the moment, yeah, we got some conversion. And inside what was nothing. On the autoclave, yeah, we got a ring which was the color of the catalyst. Yeah? So the homogeneous catalyst was decomposed. Yeah? In fact, the ring was maybe some nanoparticles. And in that moment we said, okay, let's do some nanoparticles in that case. Yeah? And Walter said, okay, I'm just interested right now because he had a pro solution to use ionic salts, solvents, yeah, and to synthesize rhodium, yeah, under this supercritical condition in the presence of the ionic solvents. And he got such kind of particles. We tested initially to see what is happening in a reaction, which doesn't matter because such reaction we can do on doesn't matter which kind of catalyst, yeah. But what was interesting in that moment, yeah, we got turnovers much higher than we got on the other particles. You will say, okay, nothing surprised because they are nanoparticles, they are directly obtained, they have a high external surface area, so they would be indeed reactive. But when you introduce this in this reaction, it was possible, yeah, to got the hydrogenation of this double bond. What is important? We got again, if you look to the typical electron microscopy, there are nanoparticles. But when you go to X pairs, you see that also in this case, you have not zero valent rhodium. To have zero valent rhodium, you have to follow for these nanoparticles the procedure proposed by Bornemann using borohydride to be sure that you get such a reduction. But when you do the reaction we have done, you got this. We compared indeed, I didn't show here the results with rhodium indeed prepared using borohydride, and it was zero. Yeah? And after that, yeah, sorry, I will come back to another point which is extremely important here. We were able, yeah, to hydrogenate because Walter is very well known for CO2 supercritical condition, and he said, why not to try to repeat this hydrogenation, not only hydrogen, but to repeat this hydrogenation to me in CO2 and hydrogen. And we were to Walter and we repeated this reaction. And what we got, we preserved, yeah, the cis double bond unaffected, but instead we have hydrogenated the aromatic ring. From thermodynamic point of view, it's clear, it's unusual because when you will hydrogenate styrene, as example, yeah, you will hydrogenate the double bond and you will keep this. What was the secret? Something was already proposed also by Baker, who was also interested in CO2 pressure reaction. And what we found? During the reaction, CO2 with hydrogen on this catalyst is generating CO. CO is partially poisoning the rhodium, so it's not an invention. It's a classic chemistry. It's partially hydrogen poisoning the rhodium, and rhodium in that case is not able to do the typical hydrogenation. So another case in this case was also nanoparticles. We were in that case enthusiastic in this case, and we said it it was a procedure proposed also by Goneman, maybe, I don't know, 18 years ago, when he published in Angewandte that it was possible for the famous asymmetric hydrogenation, it was possible not to introduce synconidine on platinum supported on alumina, but on the contrary, to use nanoparticles modified with synconidine. And he succeeded, and he get very nice enantiose selectivities. Now, typically in the metal, there are people are using bidentate ligands. So our scope was to reduce, like in the case I presented with Walter, to reduce the metal, and nanoparticles, like any isolated atom, should be stabilized. And to stabilize, you need a ligand. Yeah? Either you need a ligand to stabilize directly the metal or nanoparticles. For nanoparticles, there are not presented results, that we try to see if the stabilization of the metals could be directly achieved with this rhodium binampine. And as you see from the results, we succeeded. And we have also demonstration that palladium was indeed modified by this. Now, the last example I will show you, which is also kind of insertion, it's results we published 1 month ago, when my friends from Prague, Peter Zasama and Zdenek Sobalit, they said, okay, we are able to produce some hierarchical dealuminized zeolites, yeah, using a procedure which is very close to the procedure proposed by Krein de Jong, but in which they claimed that the two acid centers are nearby one to the other. And the idea was, are we indeed able to use this to demonstrate that we can increase activity and selectivity? And we look here at the characterization of this kind of materials. Yeah, they are indeed mesoporous, they are indeed dealuminated, so they have all the properties. Yeah, but the problem was, are we, repeat, indeed able to do this? And we checked, yeah, in our laboratory, two things. One, cracking of N-hexane, which remains a very important reaction. And the other was one reaction which was also investigated for the time here in this house, which was acylation reaction, which was a long time investigated. And we look at acylation of anisole with acetic anhydride. So, and in both the reaction, yeah, we got much better results than comparing with other zeolites. So it's again a problem of insertion, of the capability to insert in a proper way and kind of acidity. Because when we insert, yeah, you introduce, the inserted species will be, as I demonstrated, always acid species. So this is the schema of this kind of material. So, in conclusion, yeah, I hope I was able to show you the fact that a proper preparation, that means in the case of metals, looking for a proper dispersion and the proper ratio between reduced and oxidate state, yeah, will provide you a metal which might be a very good catalyst in a certain reaction. So the problem is you have to be enough patient, yeah, to identify these two properties, yeah, and I'm sure that each metal can provide much better performances that are reported to now. And we see, I repeat, at least in the case of chemistry of gold, which was in Northmont we investigated many evidences, and the paper of Avellino will provide more evidences. And even more, yeah, you can control. I show you even in the case of iridium, we can induce a certain kind of acidity, but even in the case of well-known materials like zeolite, yeah, you can still have possibility to control the acid-base property and the distribution of these Lewis acid sites to generate better performances. I have to thank to many cooperation. Yeah. With Chris Hardaker, we worked for the ionic liquids. We are in preparation with a new book on this field. With Ryan, nanoparticles. With Walter, I already showed you. Jean-Pierre Genet and Véronique Michelet de Paris, they gave us the molecules for the baric rust I have presented. They are the two people from Erlangen who help us with the in situ expert measurement. Petra and Zdenek are very old friends of mine, and so we get a good cooperation. Pascal, I have worked on different fields. Paul Grange will stay forever, my friend, although he passed away because he's a Samsung. And I also thank a lot to Pierre Jacobs, which I had extremely nice discussion. Yeah. There are few people with such a huge culture of catalysis as Pierre Jacobs is. Simona Coman is my co-worker now, his professors. They had my PhD, which were involved. Humboldt and several governmental and also FP7 projects. So I thank you very much for your very kind passion and attention. I hope you like it.